Hi, I'm Norman Wildberger. Today we want to talk about the natural unit for a turn angle when we're talking about moving around a circle. There's a natural unit here. And when we investigate things from this point of view, a lot of things simplify. But we have to still acknowledge that there's an approximate aspect when we're dealing with angles, no matter what unit system we use. Okay, so the obvious unit for angles is that we go around once. That's a turn of 1. And we might denote turn or turn angle with the Greek letter tau. So we could call that a turn angle, or maybe T angle, or maybe tangle even. Those are just various possibilities. So what we're doing here is we're really acknowledging that when it comes to going around a circle, there is a God-given canonical unit. It's not 360 or 400 or 6.28318530717 otherwise known as 2 pi, or anything else. It's just going around once. It's just the way it is. And a natural question is, what should we call this unit if we want to give it an actual name? So as opposed to degree or grad or radian, etc. Well, I think a good suggestion, which was given to me by Vincent Marciante, is let's call it a circ. So for example, from here to here, that would be a turn angle of tau equals 1/4 or 1/4 circ. This would be minus a half circ. This would be 2 circs, going all the way around twice. So I think that's a nice addition to our tool chest of terminologies for angles. So now we have a new, more canonical unit and a name for it. Now, getting at turn angles precisely is not something that we can do very much in general. So typically, turn angles are things that we can only get at approximately. So we can specify sort of intervals, but nothing much better than that. So for example, here is a 0.10 on the unit circle. Here's a 0.513, 12/13. We might be interested in describing what this turn angle is. How many circs is that? So that's some fraction of 1, but what fraction is it? Okay, well that turns out to be something that we can't actually get our finger on precisely, and that's just an intrinsic aspect of circle geometry. Circle geometry just has a complexity that linear geometry doesn't. So to understand that, we'll have to talk a little bit about the Euclidean algorithm and the connections with continued fractions, which I hope you're going to find interesting anyway. And then we'll talk about this very big difference between essentially linear and circular displacements. There's a very big difference between the line and structure and the circle and structure in terms of being able to get at displacements on those two things. So let's talk about the Euclidean algorithm for obtaining the greatest common divisor between two numbers. And you might wonder why this has something to do with the problem of describing turn angles. And the reason is because we're comparing two things. We're comparing a turn angle of 1 to a more general turn angle. And that's not really that different from describing the relationship between two segments, say this segment and this segment. And that's a problem that the ancient Greeks were very interested in, trying to compare how these two things are related. And the Euclidean algorithm really plays a big role in that. Okay, so these days it's usually thought of in terms of arithmetic. We're interested in the greatest common divisor of two integers, two natural numbers. For example, 203 and 1001. Now if we had prime factorizations for those two numbers, we could just read off the common primes. But without that, there's a certain algorithm that Euclid laid out very clearly for us. So what you do is you take the bigger number and you divide it by the smaller number. So 1001 turns out to be 4 times 203 plus a remainder of 189. And this is the division algorithm of Euclid. We know that the remainder is going to be less than the quantity that we're dividing by. Okay, great. Okay, now what we do is we look at the 203, the thing that we just divided by, and this new remainder. And the idea is that whatever common factors these two original numbers had, they're going to be shared by these two numbers. So we repeat the process. We take 203 and we divide it by 189. In this case, it goes once, and there's a remainder of 14. And then we continue. We take 189 and divide that by 14. It's 13 times 14 plus a remainder of 7. And then one more iteration. We divide 14 by 7. We get 2 times 7 plus a remainder of 0. And at that point we stop. And the last non-zero remainder that we obtained, in this case 7, is the greatest common divisor of these two numbers. So that's the result of the Euclidean algorithm. In fact, we can check that 203 is actually 29 times 7, and 1001 is 143 times 7. So yes, these are both multiples of 7. And the Greeks thought in terms of commensurability. They didn't think so much actually of numbers. They thought rather of segments. So let's look at the same problem the way the ancient Greeks probably would have thought about it. We have two segments. This bottom one here, that would be, let's say, the longer one, say 1001. And this segment here, 203. And we're interested in how can we get a smaller unit that makes these commensurable. In other words, a smaller unit such that each one of these is a multiple of that smaller unit. And we're interested, in fact, not just any old such unit, but the largest possible unit that has that property. That's exactly what we're doing up here. And the steps in the Euclidean algorithm can be translated to a geometrical procedure. So when we divide 1001 by 203, what we're doing is we're asking how many of these segments will fit into this big one. And we can get at that. There's one of them, two of them, three of them, four of them, and then there's a remainder. So we can actually construct that by making this sort of rectangular business here. So this is a square, okay? So we're going up perpendicularly here, and then we go up at a 45-degree angle, or I guess a 1/8 turn. And then we have a square here. So we are guaranteeing that this is the same as that. And then we can do that again, and again, and again. So there's 4 copies of the 203, and then there's a certain remainder. Okay, then what we're doing at the next step is playing the same game, but now with 203, which is now this side here, and this new shorter side, which is 189. Okay, so we're asking how many times does the shorter side fit into this longer side? And we can get at that by making a square. So here's a square. That's showing us that the 203 is 1 times the 189, and there's going to be a remainder here represented by that little blob there, that's 14. Okay, so then up here, the next stage, we've got 189, so that's 189 in that direction. And we're asking how many of these 14s will fit in 189. So the division again is geometrically represented by these bunches of little squares. They're each of side 14. There's 13 of them. And then there will be something left over. And the thing that's left over, it's getting hard to see, but if we magnify just this corner here, you see something like that. So here's that last square there, and then here's what's left over, and that is side 7. Okay, and then the very last operation tells us that we should take the 14, that's 14, and that's 7, and ask how many of these 7s fit into the 14. And there's exactly 2 of them. And at that stage, things sort of end because we get an exact division with no more remainder. And that last little quantity, that little part there, which is on this picture, just that little part there, that's the 7. That's then the common divisor of the 2 original numbers that we started with. So geometrically, we found that this unit here, which is just this little part there, has the property that a multiple of it is the original segment there, as well as there's another multiple that gives us the original segment there. So that's a kind of a commensurable quantity. That demonstrates the commensurability of these 2 original line segments. So this is the kind of thinking that the Greeks would have done, but these days we think more arithmetically, and we think in terms of subsequent divisions, moving down to get at this greatest common divisor. But the 2 stories are very parallel. Now this algorithm for finding greatest common divisors is very close to a beautiful topic called continued fractions, which is something that I haven't really talked very much about in my video series. It's something that I should talk more about. So here's a good place to say a little bit about that. So continued fractions are a very nice sort of alternate way of thinking about representing numbers or quantities more generally. And I want to show you how the calculation that we've just done, taking the greatest common divisor of 1001 and 203, how that actually translates to a continued fraction expansion of this quotient 1001 divided by 203. So let's see how that goes. So we're just going to look at these lines one at a time. The first one we can rewrite as 1001 divided by 203 is equal to 4 plus a remainder of 189, or in other words in fractions, plus 189 over 203. So we're just rewriting this equation by dividing everything by 203. Now, this quantity here is less than 1. The division algorithm necessarily gives us that because the remainder is always less than the quantity that we're dividing by. But what we're doing when we're going to the next step is we're then taking these two numbers and dividing the bigger one, this one here, by the smaller one, this one here. And we can think about doing that by taking this fraction here and rewriting it as 1 over its reciprocal. So this is 4 plus 1 over the fraction 203 divided by 189. Then what's in the denominator here is just something that we can express using this formula. It's actually 1 plus 14 over 189. That's what this line is telling us, that 203 divided by 189 is 1 plus 14 over 189. And then we can do the same thing. We can rewrite this by taking this fraction, which is less than 1, as it has to be, and rewriting it as 1 over 189 divided by 14, so 1 over its reciprocal. And then this 189 over 14, the result of that is the next line. The next line tells us that if we divide 189 by 14, we're going to get 13 plus a remainder of 7. So here, I'm going over here, we're going to get this thing here, the 189 over 14 is replaced with 13 plus 7 over 14. And then the same kind of thing, we take the last fraction that appeared, which is less than 1, replace it with 1 over its reciprocal, and then rewrite this reciprocal according to the next line. The next line tells us that 14 is 2 times 7, so we can replace the 14 over 7 with just 2. And there will not be a remainder of anything this time, so just 2. So when we've finally gotten to this stage here, we've rewritten the original fraction, 1001, divided by 203, in terms of this kind of nested, curious fractions, where the numerators here are always 1, so there's 1 over something, and then what's here is a number plus 1 over something else, and what's under there is a number plus 1 over something else. And in principle, this could keep on going, quite a number of steps. We can record here the information by recording just the integers that are appearing here, the 4, the 1, the 13, and the 2. And this is the standard notation for that. So we write that 1001 over 203 has the continued fraction expansion 4 colon 1 13 2. The colon sort of separates the integer part, so that's the integer part, and then these numbers here are the subsequent things that appear in the denominators of the various 1-overs that appear subsequently. So if you open, say, Wolfram alpha, and you ask it for the continued fraction of 1001 over 203, it will spit out exactly this for you. You might like to do that. That's using this wonderful tool, Wolfram alpha. It'll spit out continued fractions for you very easily. So this is a very nice alternate way of thinking about a fraction, is to rewrite it like this, and it actually is very useful to simplify things, because if this was a little bit too complicated for us, let's say, we could simplify things by removing some of the more detailed parts, the things that are sort of nested down here. So we could just rub out that a half. If we rubbed out that half, well, we'd get something that's simpler, but still not too far from the original fraction. Now, any rational number has a continued fraction expansion. And in the standard treatment of mathematics, where we talk about irrational numbers, it's generally thought that irrational numbers, whatever they are, also have continued fractions. It's just that they happen to go on forever, typically. Okay, so for us, that's problematic, but let's at least touch base with the usual story. So a very famous example is pi. So pi has a continued fraction expansion according to the usual story, and it's given by this: 3, and then the semicolon 7, 15, 1, 292, 1, 1, 1, 2, 1, 3, 1, 14, and so on. It's kind of interesting because most of the numbers are reasonably small, except for that 292 there. It seems a little bit odd that it's there. Okay, so how does this help us when we're working with pi? Well, actually, knowing the continued fraction expansion certain ways is really great for quickly extracting approximate intervals in which pi lives. Okay, so how does that work? So let's say, for example, that we just truncated here. So took 3, 7, and 15. Well, that's corresponding to the continued fraction 3 plus 1 over 7 plus 1 over 15. And then if we don't know what the next one is, then the next possible thing would be 15 plus something. So the next closest one would be what you'd get when you just bump that up by 1. So let's say that would be 16. So it's telling us that pi is actually sandwiched between these two very finite concrete rational numbers. This one here turns out to be 333 over 106. You can evaluate that. And this one is actually a very famous one, 355 over 113, which is a famous approximation of pi that was discovered by a Chinese mathematician. Now, these are all in quotes as far as I'm concerned, because pi is not really an exact number. And I don't believe in some infinite expansion like this, but I do still acknowledge that finite expansion like this can be very powerful and useful. So continued fractions give us efficient approximate bounds to irrational quantities, and they provide us really with an alternative way of thinking about what irrational numbers are. Right? They're brackets, they're ranges, and the further you go, the tighter the intervals are that you're getting. So every one of these things gives you a little interval. And so this is actually a beautiful thing because it's independent of the base. If you memorize pi in the usual base 10, 3.1415, that's base 10. But if you go to a different base, go to sexagesimal base or base 2 or base 8 or whatever, then you're going to get a different expansion. But this is actually sort of independent of base. We're writing it in base 10, but that's irrelevant. It's just that these natural numbers are kind of canonically associated to pi. So there's really something sort of foundationally more fundamental about continued fraction expressions for numbers than the typical way that we write. But having said that, we should not make the mistake of thinking that it's an easy arithmetic. So if we shifted to doing all arithmetic with continued fractions, we'd find some aspects would be a big headache, because even doing addition and multiplication and so on with continued fractions poses some serious challenges. But nevertheless, it's a very important tool, conceptual tool for us. So now I want to connect this back to the original problem of trying to get at turn angles. Let's say we have a circle here and we have 2 points, that one, and we're interested in this turn angle. How many circs is that? So we know that's one circ all the way around. How would we go about getting some kind of estimate for the number of circs involved in that particular turn angle? Well, if we just have the circle in front of us and just sort of basic tools of construction, here is the basic principle that we should look to try to exploit. That what we can do is we're doing really the same kind of thing that we're doing, that Euclid did when we were talking about the commensurability of line segments, except that now we have to kind of go around a circle as opposed to going along a line. So, for example, the first thing we might be interested in is, let's say, finding out how many of these turns are in the big turn of 1. Right? That's sort of like dividing the bigger one by the littler one. So what we're kind of really doing here, if this is tau, let's say, we're trying to get at what 1 over tau might be. The big one divided by the little one. So how do we do that? Well, it's a division, okay? What we have to do is we have to ask how many of these things fit inside here. And so we have to actually make a construction, sort of a parallel to what we did in the Euclidean linear case. But now we're in the situation of circles. So how do we duplicate such an angle? Well, one way is to draw a line segment like this, if you know the center, and then you can go perpendicularly to this thing that you've just drawn. Perpendicular, maybe like that. Okay, that's perpendicular there. Then this point that you're going to get there is going to be an equal turn angle from here to here. So this is tau, and this is also going to be tau as well. All right, so we've duplicated our turn angle in this fashion by exploiting radius. Now another way of doing this, if we don't actually have the center, say, but we just have this point here, another way of doing that would be to take the tangent at that point. So if we just have that point up there and we can calculate its tangent somehow, then we can get at this line here by just drawing a line that's parallel to the tangent through this point here. And that's another way of getting this point over here. All right, so let's try that a couple more times. So let's say that, well, that's approximately the tangent there. And then we're going to go parallel to the tangent through this point here. Okay, say it's roughly something like this. So we get another point over here. So that would be yet another equal turn angle of tau. And then we could go one more time, roughly like here. We could take the tangent there and go in this direction here, maybe down here, and then go over here, do the same thing. So by the time we've done this, we would see that the original tau sits inside 1 how many times? Once, twice, 3, 4, I guess 5 times. Okay, so 1 over tau would be, in this case, 5. But then there's going to be a remainder. So it's like dividing 1 by tau, you get 5, and then there's a remainder. What's the remainder going to be? The remainder is going to be this new turn angle, that one there. Let's call it sigma or something like that. All right. So now we're in the same kind of situation that we had with the linear case. We take out our multiples of 203, we get a remainder of 189. So that's like the 189. And then we have to ask ourselves, okay, now what's the commensurability between the tau that we just used to divide and this new remainder? Okay, so we would then be in a kind of a similar situation of then having to divide the tau by sigma. In other words, okay, we're going to get something here, and then we have to, I guess, okay, it'll have to be plus sigma over tau. Okay, and then what we'd want to do, parallel to what we did before, is rewrite the tau, sigma over tau as tau over sigma instead, and divide the tau by the sigma. So we would be in the same kind of situation of then having to say, okay, how many of these sigmas fit inside a tau? And we could do that by taking that sigma and moving it over here and counting how many of its translates or rotational translates fit inside the tau. So you can see that we can do something very parallel to what we did in the linear case, and we could get at the relative sizes of these two turn angles, the turn angle of 1, which is our basic unit, and the given one tau in this way. So this is a geometrical way. You could actually do this geometrically and then sort of narrow in, getting essentially a continued fraction for this ratio of 1 over tau, or ultimately tau. So when you're working with turn angles, there's necessarily an approximate aspect, because in the circular case, as opposed to the line case, you're almost inevitably not going to get a finite occurrence. It's not going to be that this thing stops. Okay, you're going to keep on getting smaller remainders and then smaller remainders. And this situation is intrinsically incommensurable. Okay, that's the typical thing that happens with circular things. And if you have any rational point on here, any two rational points, then chances are it's going to be incommensurable with the turn. So you're not going to be able to pin down an exact value for the turn angle, just the way it is. So while in principle, the parallels between linear commensurability and rotational commensurability are, there are parallels there. We must be conscious of a very big difference between these two situations. The big difference is that in the linear case, segments can be equally subdivided, whereas in the circular case, we cannot equally subdivide circular arcs in general. So what do I mean by that? So here's a line segment. Suppose that we are interested in dividing this line segment into 3 pieces. We want to divide it by 3. How can we do that using just relatively simple constructions? In fact, we can do this just using a notion of parallelism. So what we can do is we can create an auxiliary line here, and we can find any point on it, and then we can duplicate this segment. And you can do that with parallel lines. For example, I could have another parallel line over here, parallel to this one. I could go like this, another parallel line like that. Okay, now I've duplicated this segment here over there. Okay, now once I've got that, I can then duplicate it back over here. So I can go like this, and then another line parallel to that, and then that'll guarantee that this is a copy of that. So this is the same as that, and this is the same as that. And then I can repeat this. I could also go like this, and then something parallel to that, and that would give me this point here. So just actually with the straight edge and notion of parallelism, I'm able to create a sequence of equally spaced points on this auxiliary line. Okay, and then I can take that auxiliary line and the line I'm actually interested in dividing by 3 and draw some lines. So I can draw that line, and then I can draw a line parallel to it through this point, and another line parallel to it through this point. And if I've done that nicely, then I would have these 3 points here, all together, 2 interior points, and then these segments would all be equal because these ones are equal. Okay, so this is a standard aspect of Euclidean geometry, that given a line segment, if you want to divide it into 3 or into 5 or into 29, you can do so just by essentially exactly this story. But crucially, you cannot do anything like that over here in the circular case. What you can do the first kind of thing that we did. So you could take this point here, and let's go to the green one. Say create some other arc, and you could duplicate this one. You could duplicate that no problem. You could duplicate it once more. Okay, that's basically what I showed you in the previous slides, how to duplicate a turn angle. So these ones are equally spaced, no problem. 1, 2, 3 equally spaced segments. But there's no way of taking these 3 equally spaced points and somehow connecting them with the actual arc that we're interested in to trisect this arc here. Cannot do it. There's no clever way of doing this. People have been thinking about this for thousands of years, okay? How to trisect an angle, a famous problem from ancient Greek geometry. But it's not just trisecting that you can't do. You can't divide a segment essentially into anything, really. Even bisecting it is, bisecting you could possibly do if you have if you allow ruler and compass constructions, but that's arithmetically cheating as well, in fact. So even bisecting is problematic arithmetically, but anything further than that, like dividing by 3 or 5 or 7 or like that, is completely impossible. Okay, so that's a very, very big difference. So when you want to divide this into 3, of course you can do it approximately, sort of eyeball it. Okay, there, I've eyeballed it. I've divided up into 3. And that's essentially what you're doing when you stick a protractor there and, you know, make some measurements and do something. You're just doing something approximately. The point is there's no exact procedure for doing this. There's a huge difference between the circular and the linear stories. And when we work with angles, what we're doing is we're pretending that that's not really true. We're shielding ourselves from this reality that there's something we cannot do. We just say, oh, that's an angle theta. Now consider theta divided by 3. There, we've trisected the arc just by dividing the angle by 3. But you can't actually do that. And I think that's really important to understand, that when we're working with circular things, for a lot of situations, especially when angles are involved, you're working in approximate geometry, and there's just nothing you can do about it. Now for our next video, I'd like to go off in a different direction and talk about isometries of the plane, Euclidean plane, and also relativistic plane. So touch base again with some chromogeometry from a group theoretical point of view. So I hope you'll all join me for that. I'm Norman Wildberger. Thanks for listening.